forgot. Okay, three main approaches right until now: the Coulomb's law, the electric field, and the Gauss law. And but they are mainly vectorial, and sometimes they're very complicated to describe the directions, right? Since we are dealing with vectors. The main idea now of this new method to calculate, find the forces involved, right, in particles with charges, is using the an energy based approach. And for that, right, every time we talk about energy, it's very common for the physicists to calculate, for physicists and engineers, calculate the work, right, on the system. And you know the work is given by this scalar product too. So we are interested in the scalar product between the force acting on this system times the displacement, right? So not times, this is a scalar product. And this is relatively easier since this is going to give you one scalar. But to reach this point, right, is sometimes it's kind of complicated. Why? Because, well, from time to time, this product here, right, this product, scalar product represented by, that I represented here, is not so easy. And also, the magnitude, man, and the direction of this vector f is also sometimes can be very complicated, especially when you have like multiple charges, and when you have like objects with a kind of not objects without symmetry, then it's going to be kind of difficult. And also it depends if you do some, if you are trying to calculate the work in arbitrary paths, sometimes it's very complicated to do. You have to break it down in smaller parts and trying to calculate and the work. This can be difficult. But how then, if this is really difficult, I said that we are skipping like the three first methods to something that is easier. But at the same time, now I'm saying that I have a, even for if I try this energy based approach, I'm going to have some problem. But what is the solution then, right? Just saying problem. Come on, man, show me some, give me some solutions. So the solution, guys, is thinking about something that we call potential, right? That is going to be a scalar quantity. And we already know about this, right? Let's go back a little bit and let's recall what we learned in mechanics just, I don't know, a couple months ago, right? I don't know if you remember that. You do. And since we are working with electric force, and you know for sure, we are deadly sure, we are exponentially sure that the electric force is a conservative force. We are going to recall what we know about conservative forces in nature, and we are going to use that to find a way to express this potential for one charged particle. So let's go, guys, and let's start here with remembering, right? What is the properties? What kind of properties you have like a conservative force has? So the first one, as you can remember, is that the curl of a conservative force, this is going to be the zero vector. So this is the first main property that you have. What is the second? And this is the consequence of the first property. Any conservative force, right? The work of a conservative force over a closed path, this is going to be zero. What does it mean? That means if you are moving, I don't know, any object here, right? From A to B, A to B, and then back to A. We are doing like this. Let's put one in blue. You are moving like this first, right? And then you're moving like this, using applying a force. Doesn't matter the force here. Right? Doesn't matter the way you go. If you go like this, if you go like this, and then come back here. Doesn't matter if you go like this, or if you go like this, come back this way. This work is going to be zero. That's the main property, one of the main properties of a conservative force. What is the third property then? The third property says that the work done, right, between in this kind of conservative, the work done by this conservative force actually is way easier to calculate instead of concentrating here, right, in this scalar product. And this is something that we are actually going to use. We're interested in this particular part. Instead of using this scalar product here, because the force is conservative, I'm not going to prove that. I guess you guys have seen this in your last physics course. We can calculate the work as just the minus variation of the energy. I don't know if you guys remember that. You can represent for the gravitational force in this case here, this as being minus mg delta y. That means if you have, right, guys, if you have something being moved in a gravitational field, y, the gravity points downwards here. Have the weight on this particle right here, and you are moving this from this initial point here to a final point there. So the work done here is just the weight, just the variation in this. We call this potential energy. We just have this. That's the easiest way to calculate. Because now this is, you just have to consider one of the points as a reference. For example, you can say that this is the reference, and you can use actually just this variation right here, gravitational field, to calculate the work. And then we got rid of any considerations about like the direction magnitude of the vector, or the direction magnitude of the displacement, and so on. This is purely scalar, and it's very easy to calculate, right? And what is we said there is actually that this one here, we call this part here, put one color for you, we call this one as potential. We call this potential. This is potential energy. Please do not get confused here, guys. Potential and potential energy are two different things, right? So you can actually, we define there the gravitational potential as being this variation of energy per mass, or G. Why? And why is this so important? Why is this concept very, very, very interesting? Let's take a look on that. Let's keep this in our minds for the time being, but let's go a little bit further. Let's put here the last property of conservative, right? If force is conservative, that means we can write this force as the gradient. It's a very interesting. This is a very interesting property. We can write this as minus the gradient of the potential. And as you recall, I think most of you guys recall, if you don't, please let me know that the gradient here, these are partial derivatives, and this is a vector, right? This is going to be the del x I hat del y j hat plus del z k hat applied in this particular field, right? This is going to give a vector, of course, but this is a very easy operation since it's the first order partial derivative, and this is a scalar function. That's very, very easy. But let's keep this also in mind, because those properties are going to be very, very useful for us to. Again, let's elaborate a little bit more, right, about this idea of the potential. What is exactly the potential? Let's imagine here that you are rising, just elevating here this box, right? I just put here like a stair because as you remember here, just to emphasize that the work, right, doesn't depend on the path. I put, considering now a box going from the first step here to the last step, and since this doesn't depend on the path, it would be the same like going this completely straight, right, from point on this point here, from point A, point B. We could label each one of these steps here using what you know, right, about the potential energy, right? If you are considering, for example, like a box of 2 kilograms, you're going to have for each step here like 10 joules of energy. First step, if I'm considering the reference here, this would be 0, and then you're going to have jumps here. I just label every one, considering like the gravity goes to 10 meters second squared, and you're going to have 10 joules, 20, 30, 40 until 80, right? You can have this very easy to calculate. You know that actually the potential energy, right, is going to be dependent on the mass, of course. This is what I put here. This label here is only valid for these boxes here, the box with 2 kilograms of mass, and is going to depend on this height. But we could normalize this, guys. It could normalize, for example, if I normalize what I already know here, normalizing by mass, I could take this here, this expression, and I could normalize this by mass. Here, have here, and if I normalize by mass, I'm going to have now something, right? That actually has no dependence on the mass anymore. I have one quantity here that's only going to depend on the space. So this is the potential. So now instead of we are allowing for every point in space, right? We are allocating for every point in space, we are allocating a certain quantity of energy per unit of mass. And this is what we call gravitational potential, or just potential. We call this potential. And why is this is good? First of all, because of course it doesn't depend on the mass, right? This is just a property of the space itself. And this is good because it's a very similar thinking, it's a similar idea of what he did with the electrical field. The electric field, remember guys, let's go back to electric field. It's exactly the same here. Remember, when you normalize, right, the Coulomb force by the test charge, what we have some now is that actually we have a certain amount, right? You have a certain amount of electric field for every point in space, and so all you have to do, right, is just multiply the value that you have there by the charge itself to find the force. So it's very easy. Remember this one. So this is a similar way. This is a very similar idea. What you do here is considering now that this point has a scalar quantity associated with this, is spatially associated with it. And in this case, this point is going to have, for example, 5 joules per kilogram and so on. So if you have, of course, if you have like a mass of 2 kilograms, the potential here, just have to multiply this potential by this by the mass. This is going to be 10, then 20, 30, 40, so on, like we found here. But in this case, now you have that this is valid for any arbitrary mass, right? You can choose it. If now I have like a mass of 4 kilograms, you would have here 20 joules, 40, 60, so on. It's way easier. Now you have something, right, that depends on the position. So this the greatest advantage now is that actually this is a scalar quantity, and is independent of the mass, right? This depends only on the position. So as you can see, this is going to be very easy to calculate the work now. And you know that the work is related with the variation in the potential energy. And you know now that the potential energy is related to the potential. So you just have to relate them, and you have a very easy way to calculate the energy, and then the electric field, and then the forces acting on the charges for it. In this case, guys, of course, since I've been dealing this since lecture 1, we know, right, that the electrostatic and the gravitational fields, they are similar fields because they keep similarities, right? They have the same mathematical form for the forces. They have the same mathematical relations for those forces, and they have exactly the same mathematical formalism for their fields and so on, and their conservative forces, we can actually generalize that for the electric potential. The electric potential is going to be exactly the same. We are going to allocate a certain amount of energy, but in this case not by mass but per charge. And in this case here, so all you have to do when you are interested in find what we call the electric potential is you just have to remember the electric potential exactly the same that we did when you are studying the gravitational field. It's going to be the energy, quantitative energy, right? Joules per coulomb. This case here was by kilogram, so the only difference is that this unit, guys, is going to have like a special name. Unit is called volts, after Alessandro Volta, who was the physicist who had this tribute to him. And this actually what you call electric potential. The electric potential, let's go put here some of our definitions that we just learned by comparing with the gravitational field. The electric potential that is denoted by V, right? This is equals to the energy, right, divided by the charge. And as you can see, guys, as you can see, this is very important thing to say. Since this is normalized, right? Let's go back one. You can see that actually this is not going to depend the charge. This is going to depend only on the potential energy. That's very good. That's the main point of doing this, right? Because then you have something that is can be applied for any arbitrary charge and not for a particular charge. That's very powerful. Okay, so this is called electric potential, like I said before, and from that we can define, as I told you, this is very important, our units here. The units are coulomb. This is called volt, and always the same letters. This can get confusing. V for volt, V for potential, V for volume, V. Damn, dude, V for velocity. I know, can get complicated from time to time. My God. And again, guys, the same like here. Let's go back to the our potential energy, gravitational potential energy, right? In general, we don't have to analyze the situation in a fixed frame of reference, right? We can analyze just the variation. So we can analyze, for example, how much energy you gain from this position here, right? This position, I don't know, let's call it position D, to this position D here, and this position here. Okay, and we are just interested in the variation, in this variation. So in this sense, we don't have to fix this here and consider like an absolute like frame of reference, since we are just interested in this variation, and you know that the energy and the variation itself are going to depend only on variations here. So what do we do? Actually, we are not interested in this kind of potential itself, but we are interested in variations, in the electric potential variation. That's the most important part. since we don't have like a fixed reference frame. This is going to be actually, if you are interested here in variation, not necessarily according a fixed reference frame. Okay, guys, and from here, you can actually say that our variation potential energy, you just have to multiply the charge by the variation, the potential difference. Okay, going on. So we've interested actually in this expression here, guys. This is sometimes is referred, I think, more popular actually than potential. Instead of saying potential difference, this is called actually voltage. Voltage, and this one is energy. Uh, Please do not get confused and mix up these concepts. Potential energy and voltage are not the same. Okay, guys? They're really not the same. Many people get confused and make the. I think this is the only thing that you have to take care when you are solving problems actually. Physics. Many people, they are not exchangeable concepts. They're, as I showed you before, they're not, right? Remember here? They're not. This one is energy. This is energy per mass. And in this case, in our specific case, energy per coulomb. So it's complete. They're related, but they are not the same. Okay, with this on, what is the relation then, right? We still are going on and on and on, but you cannot lose the big picture, right? What we are doing? Oh my God, we're going V, Q, and so on. What do we have to do? We still don't know, right? Okay, now you have something better, something easier to calculate the work, right? And from the work we can actually find the electric field. As you can recall how to calculate these variations in energy, right? If you can recall that this is going to be, we have the potential can be really written as minus the work. This variation in energy. I proved here, guys. Look, I'm not going to prove now because we don't have much time. So I'm not going to prove the property 3, right? But one of the consequences of the property 3 is that actually the work for a conservative field is just the minus the variation of the energy, the potential energy in this case. Okay, so this is going to use. I'm going to leave this on your notes so you can recall how to prove. But I'm not going to prove now. I have time. I'm just going to use this result to find here like a relationship between the voltage of or the potential difference and the electrical field. This is I'm kind of interested, right? Remember, not lose the forget the big picture. You are trying to solve this here, right? Okay, we have to, so we know this, right? This is a property, our property 3 of a conservative field. We know that this one is represented by an integral, right? From between 2 points. This is going to be the force. The scalar product between the force and the displacement, the displacement vector. Right, so this, let me just write here. Three. We know that this force here is the electric force, and this electric force we can write as a function of the electrical field. This is the product of the charge by the electric field, right? You can, since the charge is constant, the charge can come outside. So this is minus q, this integral here from I to f of this scalar product or inner product or dot product, so many names, right? We can normalize, you can divide everything by q, so we are going to have this variation here, this variation divided by q, and this is going to be equal, copy here, maybe easy, use technology in our advantage, accelerate this process here. Okay, let's put this here, erase charge there, and what you have here, dun -dun. Right, you can go back to what you already know. This is the voltage, this term here, the voltage. So we can write actually this expression here as the difference or voltage equal to and this is what we finally wanna. Now we have to solve these kind of problems. Going to be relatively easier now than the ones we were doing before. And let's see how this is going to be. Okay, first thing I would like to talk are going on or solving some problems using this new concept, potential stage, potential difference or stage, is the same way, guys. Remember, let's go back here. The electric field has a very powerful way of being represented graphically. We have the same here. We're going to have exactly the same technique used. And this is what we call equipotential surfaces or equipotential lines. If you are dealing with problems in 3 dimensions, and remember, all these problems in electricity, they are three-dimensional in nature. This is going to be what you're going to have in space, right? If you represent the potential around any charge or a configuration of charges, right? This is going to be something that is three-dimensional. If there are fixed distance from the charge, they're going to have the same properties. They're going to have the same potential. Remember, the potential is connected to the space itself. So positions and space. So if these positions are fixed distance from the charges, so they are going to experience the same potential. That means that you can represent, right, this graphically. And this is called equipotential surfaces. I'm going to show you some. So I'm going, for example, for this one we already know, right? Not the equipotential surface, the equipotential lines, but I'm representing here the electrical field in purple, right? Here in purple, both are the electric field. And as you can see, the equipotential lines here, they're always, doesn't matter the case, the equipotential lines here that are represented in orange. So this is V. I don't know if I call this V1 here. This point here would have the same potential, V1 and so on. For example, here would be V1 too. So this is one thing that I have to. Of course, here you are going to have another potential. It's going to be, I don't know, let's call V2, and it's the same here. So all these lines, that is this dashed orange line here, is going to have all their points are going to have same potential, so the value is the same. And you have to remember the equipotential lines are always perpendicular to the electric field lines. So in this case here, because we have this radial electric field, what you're going to have here, the figure that is going to be formed here, is actually circles, concentric circles, in relation to the charge. And another thing that we have to say, that actually the potential in this case here that I'm just represented there is going to decrease with distance. It's going to be clear soon when I'm going to find one explicit expression for this kind of problem, right? For the potential generated by a single charged particle. For now, let's just remember that also comes from, we remember here, let's go again. Spontaneously, like a mass is going to move from a point of bigger potential to, from the big potential to the smaller. Same here. So since the field is pointing outwards, so that means that the potential in one should be bigger than the potential in voltage is bigger. That means that the you put here like a particle, charged particle, positive charged particle is going to move this way. Okay, guys, always from the biggest to the lowest potential. Very important. This is exactly the same here. Again, this is another kind of electrical field here. This is a uniform electrical field generated by a plane, for example. We studied this before. Again, if you're going to represent the potential, he wrote here surface, but in this case it's not a surface. This case is a line, potential line too, and is going to be perpendicular, right, to the electric field line. And another very important characteristic, guys, that comes from what you know about conservative fields, right? If we are moving, if a particle is moving along the potential lines, right, the work is zero for sure. How can we prove that? Let me prove. There are two ways of proving that. I'm going to prove you both of them. We know that the work, right, is equal to the minus difference in potential energy, and this is going to be a good product. The product between the charge and the voltage, right? And look, if you are considering, for example, let me put one particle here. Let's black, for example. I'm moving from here to here. Charge. So this is initial position. This is final position. Let's say that I have my reference frame. This. Why? As you can see here, this has the same potential. I don't know. Let's call this potential V. Doesn't depend on position here, since this is going to depend only on the position. Sorry, in this difference of potential. The difference. What you have here is Q by this difference, right? And since those is along the equipotation lines, so this is going to be there exactly the same. And think these two also make for this here. The work here, for example, interested in move I don't know, a particle from here to here. Work. Try to move this charge here. And we can use, and also, right, we know that the work here, force, and the force is going to be 2 electrical, that is radial for E. But as you can see here, this displacement here is going to be 90 degrees. Displacement here is going to have 90 degrees. So this here is going to be why? Because it's going to be 0. Let's see some simulations, guys, and see more of the potential surfaces. I included in your material, so you can actually play by yourself. So this, let me. Sorry, my computer is a little bit slow. My bad. Sorry. Here's the charge. As you can see, this is the potential surfaces for one a negative charge, minus nanocoulombs. And look, of course, it's very hard to represent the three-dimensional surface, right? So most problems that are going to see, the problems in your book and so on, those are cross sections, right, of the electric potential. Because it's easier to represent than actually representing the. If you put another charge here, let's put another negative charge, same this 0, that's -4. And let's show how beautiful. Oh man, I love those guys who these very nice simulations, yeah. Dalton Wash, very nice guy. Thank you so much. And here's the negative charges. Let's put 2 positive charges to see what's going to happen with potential. 4 nanocoulomb. This is 4 4. And if you have one negative and one positive, have we can right here, as you can see, guys, further I go, the potential is going, the voltage difference is going to decrease. And you can see electric like vector. Okay, so I left this in your class notes. You can play a little bit. That's very interesting. Vector node. Oh, and I put this one, Dave Neto. And you have some kind of probe. You have some The first simulation was for two. You can put one or two charges. This is for a little bit more complicated, like charge configurations. As you can see here, you have 8 charges, but you can assemble. You can make like 1, 2. You can actually adjust the charges. As you can, okay, you can play around, try your own configurations, and maybe match some of the problems from the book. The main point now that I would like to go, I would like to move the next to the next topic here. So we cover the electric field. Sorry, the potential, right? The potential surfaces, and I would like to move to the next topic that is actually how exactly can we find a mathematical expression for the electric for the potential from the electrical field from the electric field. For that, I'm going to use what we already know, already proven that this voltage, that the difference, potential difference, is expressed by this integral here, right? One, and I'm going to use this expression here that represents the electric field generated by a single charge. And then I'm going to consider the case for a positive charge, and I'm imagining that I'm moving this charge from this point here, I initial, to this point here of this point F, bigger to the smaller, lower, higher to lower potential. Okay, so let's do this. What I'm doing first. Let's put some lines here.